Hello, welcome back to Learning from a Layman. I'm Carl Christensen, here with Matt Christensen and Tim Cox, and today we're going to be discussing the electromagnetic spectrum. For those of you unfamiliar with what that is, so am I. So, that's not entirely true. I did Google it right before. So we're talking about light and the waves of light. And so I'll ask Matt to explain a little bit about their different ranges of the spectrum. I think we'll probably start there. Matt?
All right. So, yeah, the electromagnetic spectrum is quite a bit more than light.
Oh, right, because I knew that.
Well, no, you didn't, because you're a layman.
Right.
So that's why we have this podcast. Right. Anyway.
Sorry. I didn't want to. I needed to tell Tim to do something. So our biggest listener base is in Australia right now. So
Crikey.
Tim, I'm gonna need you to Australian accent the whole time.
Okay, that's I'll put it out. That's excellent. I can do that.
In an effort to alienate that listener base? Or?
Well, see, that's the trick, Matt. You make them just mad enough that they and all their friends listen in the next time. But
okay.
Our next biggest listener base is in the UK. So Matt, if you could just give us a bit of a British accent.
Jolly good.
That idea is bleeding awful. Anyway.
Oh wait, this is a family friendly program here, Matt. So.
Oh no, I accidentally cut myself just now. That's why.
Okay.
Yeah.
Okay. Sorry. Back into
Also, it should go without saying that Tim will need to stand on his head in order to capture the genuine spirit of Australian conversation, since everything down there is upside down.
That's right. It can be done. Blimey. Carl, you should keep all this in, by the way. I know you were like, but this is
I will.
that good, authentic, layman conversation that we're loved around the world for.
We're starting once again a physics, hard science related podcast. We got to start with some very layman type of banter. But
we really need to do one all about fun facts about exotic locations that none of us have been to. So
I'm down.
You're down under.
Anyway.
Down under.
Okay. Electromagnetic spectrum. I said it's light, and Matt says it's more than light. So please inform me.
Okay.
We'll be on the test.
Start by briefly talking about waves and what electromagnetic waves are. The electromagnetic spectrum is just the continuum of different electromagnetic waves by their different frequency ranges. And going back to what a wave is an oscillating field, means it goes up and down, that oscillates at a given frequency. And that frequency can be 1 beat per minute, 1 beat per second, 1 beat per nanosecond. It can be anything.
Beat as defined as the gap between peaks in the wave, right?
Yep.
Or trough, wherever you're measuring.
Yeah, exactly. And your wave has that, it has that wave shape with a peak and then descending down to a trough and rising to another peak. And it does that at a regular interval forever. And that is the interval between those peaks or between those troughs or whatever is the frequency of that wave. The electromagnetic spectrum is made up of every wave you can imagine that is an electromagnetic wave at every frequency, starting with extremely low frequency waves that go between peaks and troughs at about 1 to 3 cycles per second, all the way up to incredibly high frequency gamma rays that have frequencies that are in the 300 exahertz range. Exahertz meaning that you have 10 times 10 to the 18th power cycles per second.
Wow.
And when we say hertz, it's Hertz. 1 hertz is 1 cycle per second. So 3 hertz, 3 cycles per second. 300 exahertz, 300 times 10 to the 18th cycles per second.
That's
It's a bunch.
yeah,
It is
that's a
a
lot.
large number.
As they say, it hurts a lot.
Nobody says that.
No.
Blimey.
Anyway, yeah. So when we talk about electromagnetic waves, what we're talking about is that peak trough oscillation of an electromagnetic field. And when we say electromagnetic field, we mean an electric field and a magnetic field. If you have a magnetic field, if you put a bar magnet on the counter in front of you and dump a bunch of iron filings around it, you'll see the iron filings start to take a series of bow-shaped shapes around the different poles of that magnet. And that's a way to visualize the magnetic field of that magnet. Now, if that magnetic field is to be perturbed and an oscillation is put into play, then you start to have magnetic waves. And anytime you have a magnetic wave, you have an accompanying electric field wave. And the reverse is true also. You cannot have a wave in an electric field or a magnetic field without the other. And that's why they're called electromagnetic waves. No kidding. Okay, so this is neat and interesting and stuff. But all of these electromagnetic waves, they're just different ways for energy to move in different mediums. And the different electromagnetic waves can be used for different purposes. And they start, as I mentioned, at extremely low frequency waves that are on the order of single-digit hertz, 1 hertz, 2 hertz, 3 hertz.
And with those ones, we're talking radio waves, right?
We're talking waves far below what your standard radio would be, and I'll talk about why in a minute.
Okay.
And they go all the way up to those gamma rays, which you sometimes find in high-end medical equipment, particularly cancer-treating medical equipment. But the other characteristic of waves that I want to talk about before I go into all of that is a parameter called wavelength. And the wavelength is related directly to the frequency. All of these electromagnetic waves travel at the speed of light. We talk about the speed of light, but we really mean the speed of electromagnetic wave propagation in vacuum. And that's 3 times 10 to the 8th meters per second, whatever. So given that they all move at the same speed, if they have different cycles, then you can figure out what the wavelength is based on the cycles, the frequency. And when I talk about wavelength, I mean the physical distance between 2 identical points in that wave, between 2 of the troughs, or between 2 of the peaks, or between 2 consecutive midlines, whatever. That's the wavelength. And so if you have a wave that goes through 3 complete cycles every second, that wave travels 3 times 10 to the 8th meters in that same second. That means that in that 3 times 10 to the 8th meters, you have 3 complete waves. What that really means is that each one of those waves is roughly 100,000 kilometers long. And when you get up to higher frequency things like the UHF that you used to find in old televisions, you're in the range where your waves are about 1 meter long because your frequency is much higher and each wave is shorter. And when you get up to the extremely, extremely high frequency waves, the gamma rays and so forth, you have wavelengths that are about the same physical length as the diameter of an atomic nucleus. They're measured in, I don't even know, picometers, I think. Yeah. So the wavelength and the frequency, these are just characteristics of these different waves. And what this means for you practically is that if you want to generate or receive or manipulate any of these waves, your antenna that you use to transmit or generate them has to relate to the wavelength at a certain level. If I want to generate a UHF wave, which has a 1 meter wavelength, then I need an antenna that's going to be around that order of magnitude. I can get away with a half meter antenna or a quarter meter antenna or a 1 meter antenna or whatever. But if I have a millimeter long antenna, it's going to be pretty difficult for me to pick up a UHF wave. So when we talked about those extremely low frequency waves that operate in the 1 hertz range that have a 1,000 kilometer wavelength, if I want an antenna that can manipulate those waves, I need an antenna that is kilometers long. And that's totally what the US Navy did, because they used extremely low frequency waves to communicate with submarines. And the transmission stations for those waves used 2 antennas that were each 16 kilometers long. Now, it's a little bit impractical to fit in your car. So nobody else uses ELF, extremely low frequency communication or waves. But that's something to consider when you're trying to design your wave-based communication system. So.
Hey, I don't know if you're going to plan on getting into this more, but how does an antenna translate those waves into other information?
Yeah, we will talk about that a little bit when we talk about how to actually use a wave for a constructive purpose and signal modulation and all that stuff.
Right. Okay.
So, but let's just jump through the different kind of sections of the electromagnetic spectrum and talk about what they are and what they do. And we'll go from low frequency to high frequency. So, and by the way, that means that your wavelength is going in the reverse order. You're going from longest wavelength to shortest wavelength. So, as I mentioned, your lowest frequency waves are going to be in the section of the spectrum that is broadly termed radio waves. It starts down at extremely low frequency, goes to super low frequency, ultra low frequency, very low frequency, all the way up to extremely high frequency, which is EHF. This includes most of the waves that we use for communications. Your radio in your car, your satellite antenna for your TV is going to use super high frequency waves on the order of 6 to 8 gigahertz, something like that, all the way up to military satellite communications platforms that have higher frequencies than that. And they do this for different reasons and for different applications. All of these radio waves move in the Earth's atmosphere in different ways, or rather, they are reflected and deflected in different ways based on their wavelength, based on their frequency. So I mentioned some of these waves are used to communicate with submarines. Well, the super low frequency waves can actually penetrate pretty far into salt water. Extremely low frequency waves can go down hundreds of meters into the ocean. That's pretty cool. The problem is you need a kilometers long antenna to both generate and receive the signal. That's less cool. And as you go up in frequency, those waves start to be attenuated, means their signal gets absorbed more and more by salt water. And when you get past about very low frequency, VLF, where you're at 3,000 cycles per second, it becomes kind of hard to talk to something that's underwater. Now in the atmosphere, you have different considerations, and waves move, different waves move in different ways. Some of the radio waves will go straight through the atmosphere and out into the void of space forever. And NASA and other people and conspiracy theorists use these to broadcast messages out into the great beyond, or look for aliens, or maintain communications with interstellar probes, or whatever. And all of that depends on the wavelength, the frequency of that wave, and how it does and doesn't react or be reflected by the different elements in the atmosphere. I mentioned your satellite communications waves are going to be on the order of gigahertz, a couple billion cycles per second for their frequency. Well, those frequencies in general go through the atmosphere really well, and they go from your antenna that's on your roof all the way out to the satellite that's floating 40,000 kilometers away, and all the way back with very little interference, and that's great. And so you can get your TV signal like that. If you try to use a different wave at a different frequency, it will get absorbed and attenuated. So within that spectrum of radio waves, that section of the electromagnetic spectrum, you have two kind of subparts. You have what are traditionally called radio waves, and you also have microwaves. And yes, this is your kitchen appliance that heats up food, but it's a little more than that as well. When we talk about microwaves, we're talking things that range from, a couple megahertz all the way up to gigahertz, and that includes your direct TV and things like that, your TV signals of any kind, UHF, VHF, all of those things. That's all microwaves. Interestingly, the kitchen appliance uses microwave radiation, microwave waves, to heat up your food. And it does so because the resonant frequency of water is within that range. And so if you generate an electromagnetic field that matches that water resonant frequency, I don't remember what it is offhand. I think it's 2 gigahertz or something, but I'll have to have some Australian Google that for me. Anyway, when you get that resonance, you excite those water molecules, and the motion of excited molecules, it means heat. That means the water in your food heats up. That means your food heats up. That's how microwaves work.
So if you put a brick in the microwave, it's not going to heat up?
No. In fact, if you put an empty mug in the microwave and blast it, does that heat up?
I don't know. I haven't tried.
And that explains why some containers, a lot of containers, you pull them out, they're cool to the touch, but you get some that aren't microwave safe, they heat up. That means their structure is like resonates with the microwave. Is that right?
More probably, it means that the structure is thin enough that whatever food you have inside it is heated up, not only the food, but the heat transfers from the food to the container.
Okay.
So if you have a thick food carrying device, like a hefty ceramic mug, that's going to give you a little bit more insulation. If you have a thin piece of Tupperware or cheap Tupperware, and it's filled up with, soup, then that's going to transfer the heat from the soup to the container to your delicate fingertips pretty quickly. But that's what your microwave does. It works by agitating the molecules within your food because it generates a microwave wave that resonates with those molecules. And again, that molecular motion is heat, and so it heats it up.
Now, back in the day, the old, urban legend that standing near a microwave was dangerous, that's not really true, right?
Aha, so it totally is true. Depending.
What? No.
Yeah. And
so, didn't we? Tell me if I'm wrong. Sorry. Didn't we kind of learn about microwaves from like birds flying in front of old radar dishes and they blew up?
Well, I don't know.
You don't know? All right.
That seems pretty brutal, but it would in some ways make sense. So here we'll talk about a lot of this in a minute as we go forward. But yeah, all of these forms of electromagnetic radiation can have different effects on different things, and including living tissues. Radio waves in general are pretty benign. Unless you're standing directly in front of a dish that's transmitting, you're generally okay when you're talking radio waves. Microwaves, though, it's high energy radiation. If you're standing in front of a microwave relay dish, you'll get baked. Now, is your home microwave safe to be near? Yeah, it totally is. unless it is poorly made and poorly shielded. And in that case, if it's leaking microwave radiation, then yeah, that could be a hazard if you were to camp next to it for hours at a time with it running at max power. No, nobody needs to be afraid of their microwave. There are standards that are in place to make sure that microwaves are built such that they don't leak. But that's where that legend would have come from, because those same waves that are in your microwave can do you harm if you are exposed to a significant enough dose over a significant enough period of time. One of the parts of waves that we didn't talk about is the amplitude of the wave. That's the distance between the peak and the trough. And what that actually means is the power involved in that wave. Your microwave in your kitchen is a significant amount of power in order to heat up your food. The transmitter on a large ground-based satellite uplink station has way more power than that in order to generate a signal that will make it out to space and back. That's where you want to be a lot more careful about staying out of the radiation hazard zone, because yeah, that could cause you some issues. But if
well,
you
I'm
take
relieved, but
yeah,
nevertheless, I am gonna move my bed out of the kitchen
excellent,
and away from my microwave. Then.
Yeah, well, and just don't buy your microwave from. I mean, microwaves today are pretty safe. The ones that you're going to find manufactured anywhere are pretty good. If you're buying your microwave from some guy in a back alley and it's obviously like leaking parts and that's maybe where you start to get concerned. But for practical purposes, no, I don't think your consumer has to worry about that. Standard disclaimer: when it comes to microwave appliance safety, I am not an expert. I am just a layman. I am voicing my own opinion. Do not sue us if you get cancer from camping next to your microwave, you idiot.
Well, that's why the name of the podcast is what it is. It might as well just be "You Can't Sue Us." So
the full name is actually "Learn It from a Layman Who Is Legally Immune from."
Your lawsuits.
I'll have to look at the paperwork. Yeah.
Anyway, okay. So radio waves and microwaves, chiefly used for. Both of them are chiefly used for communication and for heating up your leftovers. When you go past that, you start to get into infrared, the infrared portion of the spectrum. And as we all know, this is what allows snakes and maybe velociraptors and the predator to hunt so well. It is just a portion of the electromagnetic spectrum. And right above infrared, you get into visible light. Light is a type of electromagnetic wave, and it's one that our eyes are designed around in terms of, well, our eyes act as biological antennas for that visible light. This, again, being a type of electromagnetic wave, it travels through things at different levels based on what the thing is. Visible light travels really well through the air. Not all of the radio waves do. Visible light does not travel through solid, non-clear materials. Some other waves absolutely travel through solid objects. It all depends.
This is also how we can explain the sky is blue, right?
Kind of, not really. Well,
what?
So, kind of.
Doesn't have to do with the length, wavelength of light and the way that it refracts as it hits the atmosphere.
Yes-ish. It's yeah. The sky is due because of a phenomenon known as Rayleigh scattering. And when light hits the upper atmosphere, it is diffracted by different elements, and the end result is you get blue as your predominant shade based on which light is refracted at which angle. And you may have noticed, if you have ever been outside in the morning or the evening, that the sky is no longer blue. It turns orange. And that's because at those points, the light coming in is being refracted at different angles because the sun is at a different angular position. And so you get more yellows and oranges and reds than you do those blues. But as far as what the light itself moves through, visible light does go through the atmosphere pretty well. That's why you can see stars at night, even though those light sources are unimaginably far away, millions of light years. That light gets all the way through the vacuum of space and all the way through our atmosphere down to us. The only difference between day and night is that you don't have sunlight and that Rayleigh scattering effectively flooding everything out with. And anyway, that's the next chunk on the electromagnetic spectrum scale or continuum. After that, you go up to ultraviolet, which is just beyond what we humans can see, but it's still a thing. Interestingly, we talk about ultraviolet rays coming from the sun. Turns out that the sun generates electromagnetic waves almost continuously through most of the just an immense amount of the electromagnetic spectrum. The sun generates radio signal, the sun generates visible light, as we know, and the sun generates ultraviolet and beyond. And the bad stuff, fortunately, is blocked out by our atmosphere because our atmosphere absorbs ultraviolet light and X-rays and gamma rays and so forth. And those are the next things on the electromagnetic spectrum. You have your X-rays, your hard X-rays and your soft X-rays, and then you have your gamma rays. And when you get to the gamma ray range, you're talking about those exohertz frequencies with wavelengths that are literally comparable to the diameter of an atomic nucleus. They're that fast and that short.
What are hard and soft X-rays? Sorry, I've never heard of that before.
So hard X-rays are just higher energy X-rays. Lower energy X-rays are the soft X-rays. The ones that you get at the hospital, that's going to be hard X-rays. That's what you use to see inside of things. And you use that because they are so high frequency, they go through stuff really well, like through solid things. Now, fortunately, they don't get through the atmosphere and the magnetosphere surrounding Earth. Otherwise, we would be subjected to a constant stream of high energy X-ray bombardment that would very quickly give us all cancer and we would die.
I was going to say, actually, the X-rays, even the ones that you get at the doctor, the dentist, already are a bit of a cancer concern, right? That's why they put a lead vest on you in the dentist's office.
Yeah, but I mean, yes.
I believe that's over long-term exposure.
It very much is, yes. If you camp in the X-ray machine with it on, yeah, you'll start to have some negative effects.
All right, I'm moving my bed out of the dentist's office. You can cut that if you want.
No, I think that's important so that our listeners know the caliber of people they're dealing with.
That's right.
So in general, when you take an airline flight and you're cruising along at 30,000+ feet, there's less atmospheric protection from the cosmic radiation that's constantly coming in and bombarding our planet. And what that means is that you get more X-ray exposure on an airliner than you do actually getting an X-ray at the hospital. So you're fine.
Wow.
Assuming that you don't literally camp in the machine. Now, is it still a good idea to put on the lead vest and stuff? Yeah, I mean, you might as well take the precautions. And no, you do not need to wear that same lead vest the next time you fly on an airliner. But the risk is low enough that as long as you're being reasonable and not getting a million X-rays a year, you should be fine.
Now, would I mean, you said the hard X-rays and the soft X-rays, is that the difference? The hard X-rays you get at the hospital, but if you're flying, you're exposed to X-ray radiation, but wouldn't that be of a lower power?
Well, I mean, I don't know that when you're flying you're getting hard or soft X-rays. I imagine you're getting both, but yeah, the soft X-rays are the lower frequency, lower energy levels. They're also a little bit better absorbed in the air, I guess. I'm not an expert on hard and soft X-rays. I'm sorry.
Okay.
So what we're saying is maybe our pilots should be wearing the lead vests.
That's what I was going to say. Like if I'm a pilot or a flight attendant, I would imagine that if that were the case, that I would have a very severe cancer risk.
No, you would not have a severe cancer risk. Again, people have done studies on what your total radiation doses are based on where you are and what you do, and airline pilots and nuclear engineers, while you might see more than your average Joe, maybe, it's still below thresholds where you need to be reasonably concerned.
Okay, so Tim can move his bed back into the dentist's office.
So
well, I wouldn't say the dentist's office, but he can move it back into the airliner.
Oh.
I just love falling asleep to the sound of two giant engines.
So unless I'm sucking on a plutonium rod, I'm probably going to be okay.
We're talking about different radiation, though, with that. And that was weirdly phrased. Carl, you should definitely edit that out. Anyway.
Carl, you need to make also like a blooper reel of all the times you say edit that out.
Well,
yeah.
Maybe.
Just like pack it all into like 60 seconds.
Yeah.
All right. So, hey, Cameron, you had looked up the microwave frequencies. What was that again?
I did look at the microwave frequency. Thank goodness for our wonderful search engines. It says microwaves operate on a let me double check that I make sure I say it correctly. Yes, microwaves work on a frequency of 2.5 gigahertz. Water is actually, its frequency is actually higher than that, but they use a lower frequency so it penetrates deeper in the microwave into dishes and stuff. So they're using a lower frequency to do a deeper heat, which is kind of what you were talking about with the wavelength. So at a higher frequency, it's not going to go as deep into things. So.
Cool. Thank you. One of the things that you may notice if you have a satellite communications dish, depending on the company and depending on the frequency that they operate at for your satellite TV, you may notice that your signal is significantly degraded during a rainstorm or when there's snow or when there's any kind of significant amount of water in the atmosphere. Because water, again, with its resonant frequencies, can really interfere with the way that those electromagnetic waves are able to propagate and move through the atmosphere. Anyway,
can I ask real quick, why do high frequency waves travel through solid matter and such better than low frequency waves? Like what's going on at the atomic level or whatever that makes that happen?
I don't know, and different materials are more and less opaque to different types of waves. And I mentioned that the ultra low frequency waves, not even ultra low frequency, lower than that. Ultra low frequency is actually a named band of the spectrum. But the lowest frequency
That's
waves.
That's a great name for a band. Sorry.
Yes, it is.
Not band name, named band, Tim.
Dang it.
Whatever. Anyway, the lowest frequency waves they can penetrate salt water. That's pretty cool. And there's not, visible light, which is significantly higher frequency, doesn't do that as well to the same depth. You can get the lowest frequency radio waves down to hundreds of meters below the ocean surface. You can't do that with visible light. Now that said, gamma ray can go through pretty much anything. That's one of the great causes of death and destruction that accompanies a nuclear event. When a nuclear bomb goes off, it releases a large amount of radiation. Obviously, there's a large amount of visible light with the giant flash. There is a large amount of just everything, of heat and pressure and force. But there is also a phenomenal amount of gamma radiation, and the gamma radiation just goes through everything. You need feet of concrete to protect you from gamma radiation, and it's incredibly deadly to living tissues. It will kill you very quickly.
Okay, fact check here. If I am near an explosion and I put myself into an old school 1950s era refrigerator, that will not protect me.
Yeah, according to a recent documentary that I saw, you will be fine. And in fact, that 1950s era fridge, because it has inertial dampening mechanisms and cushioning systems, will protect you even from the physical jarring that comes when it's hurled. Never mind. Unless you are Harrison Ford or Shia LaBeouf, I guess. The fridge isn't going to help you very much.
Good to know.
Why did you even bring up that movie? It's better for the world if we pretend that one doesn't exist.
They're making another. What could go wrong?
A number of things. Anyway, so that's the different chunks of the electromagnetic spectrum. Should we talk about how you actually use it to transmit information?
Yeah, I think that's what's most interesting to me. And as the resident layman, I think I get to determine what's useful.
All right.
Layman snob.
Yeah, going a little bit mad with power there. That's okay. All right. Let's step back and look at very basic Morse code. Morse code works because you have a way to send a electromagnetic pulse at a given rhythm. And the rhythm that you send that pulse at is according to a code, a key that you have created. And you have a copy of that key, and you use that to generate a number of pulses, beep, 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 and so forth. And you give someone at the other end that same key, and they can see how those pulses have come in. They can determine the amount and length of the beeps, and they can use that key to reconstruct the information that you are trying to send. So, Tim, get your bed out of the kitchen away from the microwave. That you would translate that message into a series of electromagnetic pulses, short beeps and long beeps. And that is how Morse code works.
Bleepity bleeps, just for good measure.
Yeah, except this is family friendly, so we don't do that. Ow, my bleeding finger. All right. Okay.
We've really.
Literally bleeding finger.
I'm gonna have to put like a parental advisory on this episode in the UK. So.
Yeah, only in the Commonwealth countries. We who speak the president's English don't worry about these things.
Jolly good.
Yeah, it's gonna be huge, bigly.
Oh boy.
Anyway, so you have your code and your key to your code, and if you have the code and the person on the other end has the code, then you can manipulate those electromagnetic pulses or those electric pulses through that wire, through your key tapping, to send a message. Now, it turns out I can use radio waves the exact same way, and I don't necessarily use Morse code, but I can manipulate those waves in a given and predictable manner. And then if I tell you how I'm going to manipulate them, and I give you the key to the code, then you can look at that wave as it comes in. You can see how it is twisted and contorted and changed, and you can reconstruct the information that I'm trying to convey to you based on how I have manipulated my wave. And the term that we use for that is modulation. That's the word of the day. Modulation is the act of manipulating a wave according to some information code that you have and that your recipient has. You can modulate an electromagnetic wave in a number of ways. The ones that you're familiar with, even if you didn't realize it, are AM and FM. And that stands for amplitude modulation and frequency modulation. Amplitude modulation is simply adding power to your wave, increasing its amplitude, or taking power away from your wave, decreasing its amplitude, according to a preset code. So if I tell you that the letter A is going to be 2 big peaks followed by 2 short peaks, then I can send you the letter A based on how I modulate the amplitude of my wave. To make it even easier, I can just go binary with it, and I can send you a stream of 1s and 0s based on based on how I have changed the amplitude of my wave. And from that, I can very quickly construct any information you can imagine that you can pull out of binary or whatever. Frequency modulation is FM is just changing the frequency by a little bit. If you look at your FM radio that maybe people still have in their cars, I don't know, you dial up a radio station at a certain frequency, 97 point whatever FM, right? Well, it's not exactly 97.5. It's actually 97.45 to 97.55 or something like that. And anywhere in that range, that radio station is generating a radio wave. And if it's at 97.45 hertz, then that corresponds to a certain bit of information or a certain tone or a certain noise, whatever. If the frequency moves to 97.46 or 97 point whatever, then that corresponds to a different chunk of information. And your signal moves between those different frequencies far faster than a human can process, but your radio picks it up, and your radio responds accordingly because the transmitter has the code and your receiver has the code, and you can get the information that transmitter is sending based on how they have modulated that wave using frequency modulation. The other one that we use a lot, especially in digital communications, is phase modulation. If you think of the wave going up and down in that kind of serene pattern of waviness, what if instead of going up and down smoothly, when I get to the top, I break the wave and I flip it so that I'm suddenly, that in the very next instant, I'm now at the bottom. I'm at a trough. I go peak to trough instantaneously, and then my wave continues. Well, when we do that, we call that shifting the phase. And a shift in phase like that can be used to convey information. If I tell you that anytime I shift the phase like that, it's going to be a 1. Anytime I don't shift the phase, it's going to be a 0. Suddenly, I have a very simple code that allows me to stream 1s and 0s to you all day long. I do not physically pack a 1 onto the wave. I can't do that. A 1 is not a thing that I can imprint onto a beam of light. But I can change the beam of light in such a way that I tell you how I'm changing it, and you know that the change represents a 1, and a different change will represent a 0. That's modulation, and those are the 3 basic types, and that is how we express information by using electromagnetic waves.
Hey, so a question about that.
Yeah.
So we used to use analog frequency on the TV.
Yep.
If you wanted to, previously it was analog frequencies, and now you have digital channels.
Yep.
So what's the change in technology there, and how does that relate to the waves?
I would be going, when we talk about the internals of a radio, I'd be going out of my depth. I don't know.
Okay.
But really, when we talk about the difference between analog and digital, we're just at the very basic fundamental level. We're talking about changes in what the modulation represents. So an analog signal, if I modulate it, and it's an old school VHF color TV signal, the change is going to be a continuous change. That means analog, and it's going to represent different colors of pixel for my screen, and it's going to represent different tones that will come out of my speaker. And your TV has the gear inside to look at the waves that come in and how they are modulated, and say it is approximately this color and this sound that I should now be generating. And that's analog. When we go to digital, instead of doing approximately this or approximately that, we're now doing ones and zeros, and we then use another chunk of equipment to translate the ones and zeros to a very specific pixel pattern or digital sound or whatever. And it's just, there's a difference in the images or the sounds that you can get out of that. There's differences in the types of information that you can represent. Digital communication is going to be more precise, right, but it's not necessarily as perfectly accurate. If I want to represent a color perfectly to you, an analog signal may be able to get a color to be as accurate, even if the signal is not as precise as a digital signal. A digital signal will be extremely precise, but because digital signals they represent discrete amounts of information rather than or discrete continuums of information rather than continuous continuums of information, you may not be able to get the exact representation of whatever it is that you're trying to represent. I don't know if that makes any sense at all.
I think so. What I understand you saying is I should watch all my videos on VCR.
Yes.
That's an analog signal, right?
Yeah, it is.
And
it's reading analog signals off a magnetic tape.
Right. So generally that's going to have, obviously in practice, it doesn't have any real benefit over the DVD or Blu-ray that we have nowadays. But in theory, there are potentially ways, and that could be more true to the original content than the digital version. Is that true?
Yeah, in theory. Well, and the one place where this practically comes into play, and people can claim that they can tell a difference, is when you look at
a record.
Records, the vinyl records. Right. Audiophiles, who are much more gifted than I am in terms of hearing, will tell you that that music or sound produced from a vinyl record has a feel or a depth to it that you don't get even from the highest end digital systems. Now, me being a layman when it comes to audio stuff, I don't notice the difference. And the digital systems are so good that I think most humans don't notice the difference. But an audiophile will punch me in the face and tell me that I'm all the way wrong there. And at a technical level, they're correct, because a digital system cannot replicate. Digital systems use steps. They use discrete amounts of information. They go from one specific point frequency to another specific point frequency, and they skip what is in between. An analog system will not do that. It can, depending on the class of equipment and how precise it is, it can nearly perfectly replicate a signal or a sound. A digital system can do an exceptionally good approximation. And a digital system, in many cases, will produce a superior signal when you take into account other environmental factors like interference and attenuation and so forth. A digital signal will often be more robust. But yes, if you want that true, listening experience, for example, that analog signal can get you a level of accuracy, if not precision, that you don't get with a digital system. However, both digital and analog signals, they're all modulated to some extent in some way according to some sort of code. And the generator has the code, the receiver has the code. For a record, the code is bumps, grooves, whatever it is, and your record player reads that and generates the appropriate sound. For your CD player, it's little, it's just the information, the bumps embedded into that layer of your CD, and the little laser reads those bumps, goes, that's a 1, that's a 0, that's a 1, that's a 0. According to my little chart, that sequence of 1s and 0s means I should play an A flat, and it generates an A flat, or whatever.
Right.
Anyway, that's kind of a very basic intro to information coding. And you can do this with all manner of things, but if you want to transmit that information, you can do it with electromagnetic waves. We use radio waves for that. We use microwaves for that. We even use visible light for that with laser communications, where you point a laser at a receiver and you turn your laser on and off according to a pattern, just like Morse code. And depending on how you do that, you can very quickly convey a large amount of information. You can do this with almost anything.
Useful. Obviously, given that we've figured out how to use that across the board now in so many different ways. So cell phones, I guess, maybe we can wrap up the podcast here shortly, but cell phones use digital signals as well. But what kind of they're not using radio waves, are they? Or what,
they very much are. Yeah.
Okay.
They're down in the I don't know, a couple gigahertz band. I'd have to look it up.
Okay.
But yeah, it's and we could go into some other things that I don't actually want to go into.
Okay.
But cell phones just use radio signals. A quick Google search as I'm talking, it looks they're in the hundreds of megahertz to single-digit gigahertz, maybe, I guess. I don't know. But you could look that up.
Right.
But all they are is taking those radio waves and manipulating them according to different those different constructs that I've talked about.
Hey, and maybe this goes beyond the scope of electromagnetic spectrum discussion in general, but so, I mean, we all have cell phones, right? And if they're broadcasting using radio waves, shouldn't anyone's phone be able to pick up my cell conversation?
Okay. At a physical level, yes, totally can. The thing is that fortunately, your cell phone has the code that the cell phone carrier has established to tell a cell phone when it is getting a signal. So when a call goes out, it's coded. Part of the message that is transmitted is a code that tells which cell phone to wake up and receive it. Each cell phone has a specific carrier or user identification thing in it somehow, whether it's a SIM card or some other method. The different companies use different things. But part of that modulated signal that is being broadcast by every cell phone caller to every other cell tower in the anyway, all of those cell phone calls that are going out and are being re-reflected through the towers, they all have the appropriate information to tell which phone to wake up and receive the call. And then once that connection is made, you send your modulated signal, you receive your modulated signal, and so forth. But yeah, at a physical level, yes, your cell phone has the appropriate antenna and processing hardware to pick up every cell phone call all around you. It won't wake up because as it's receiving those signals, it's looking at that coded modulated message and going, nope, that's not for me. Nope, that's not for me. Oh, this one is from Tim. And then you hit ignore because you're a bad person. But anyway.
So, I mean, conceivably, then it can be hacked, right? Encoded information can generally be decoded by someone if they want that to be decoded badly enough.
Theoretically, sure. And in fact, if I walk around with a very expensive piece of equipment called a spectrum analyzer and a very basic antenna, I can see every signal in the electromagnetic spectrum ranging from 0 megahertz all the way up to 20, 30, 40 gigahertz. And I can see where those signals are. And then if I have the appropriate processing equipment, I can plug that into my antenna and I can receive that signal. And then if I have the appropriate codes, and I probably don't, yeah, I could get the information out of that. Thing is, though, the cell phone companies know that, and their codes are proprietary, and you're not going to break them. You just aren't. And if you do, I will be very surprised. So, yeah, it's just not something that
conspiracy theories or give fodder to those that are hyper sensitive to someone listening in. But just the idea that it is broadcasted, and but I mean,
sure,
like you said,
any wireless, the Wi-Fi that your computer uses that you plug into at the, if you go down to the Dunkin' Donuts or the Starbucks or wherever it is that you go to use the free Wi-Fi. All of that's using radio or electromagnetic waves. All of that is being broadcast to the entire, coffee shop, I guess. And all of that could be received. But practically, should you worry about that? Well, no, not really. Because you have a specific code that is unique to you that establishes that communication for you. Take basic precautions. Don't do banking at the coffee shop. That is a bad idea. But
web protocols and those types of things also help. I mean, they provide another layer of encryption and those types of
and having a VPN and so forth. But if you have the right equipment, you can see all of these different waves in the spectrum. Now, it is a whole nother step entirely that is well beyond the capacity of anyone to be able to get into decoding those signals unless they have the appropriate keys. But you can definitely, with the right equipment, see what the signal or the frequencies that the signals are at. You just may not be able to read them. Does that make sense?
It does, yeah. I think that's a good way to wrap the podcast up, unless you have other information you wanted to share with us.
No, I think I'm...
You're good.
Anything else is information for which I'm not going to give you the appropriate code. So
it's so sad now that all my TV and movies have lied to me.
Oh, what about?
That people just can't randomly pick up and listen to my cell phone call.
Oh.
That's right.
I mean,
or my baby monitor works on the walkie-talkie.
So, I mean, that was something that you could get in the old days when people actually used walkie-talkies. You would pick up other people's signals and other conversations if you were on the walkie-talkie.
Because those weren't encoded specifically. Those were just generic encoding for like anyone listening.
Yeah.
It's a public key type of situation.
Yep. Some people, or not even a public key. It's not encrypted at all. It's just, here's basic FM or AM radio, and anything with a basic FM or AM or whatever it was modulator could pick it up. People used to be able to listen in on the police bands. Maybe you can still do that. I don't know. Ham radio operators, as their hobby, they rely on being able to pick up any signal from anyone, anywhere. And, they just talk to each other all over the world. And that's fine.
Ham stands for high amplitude modulation? Or what is... Do you know?
I
don't know.
I don't actually know what ham stands
for.
Well,
okay. Then we should just ask our listeners to let us know what that means.
Yes.
Okay. Well, we'll leave it there then. So thanks, Matt, for the instructive podcast, and Tim for the inane comments, and Cameron for some instruction. Cameron's for some research, and we'll invite you guys to come back and listen to our next podcast. I believe we're going to talk about translation in our next podcast, so stay tuned for that. Stay tuned to this electromagnetic spectrum of podcast.